We're very excited to welcome back our guest speaker, Brian Day from NASA Ames Research Center. I think that, for sure, Brian, you are the record holder for the number of times presenting to this group. This is either 3 or 4. Maybe
My God, you're in a rut.
Yeah, maybe it's even more than that. I don't know, but we can figure it out. NASA Ames Research Center. I think that, for sure, Brian, you are the record holder for the number of times presenting. And I'm hearing myself. How about that? That was a unique experience.
Deja vu.
Okay, are we okay? Okay. Welcome to everyone joining us on YouTube. We're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, check the links in the chat, which will be there momentarily. Before we introduce Brian, here's Vivian with just a couple of announcements. Have you with us?
I have a feeling
these webinars are monthly events for members of the Night Sky Network. For more information about the NASA Night Sky Network and the Astronomical Society.
It's me. Hi. Is that working now? Can you not hear you again? Welcome everybody. Hi. I wanted to let you know to stick around for the end of Brian Day's talk so that we can we'll be giving you a link to fill out just a survey about what you want to hear coming up, and also you'll be entered to receive, oh, that looks really cool, one of 5 totality books by Jeff Bennett, who's generously donated them, getting you ready for the upcoming eclipses. So be sure to stick around. We'll throw that in the chat at the end. And I want to give a huge shout out and a couple of tears, because this will be David Prosper's last webinar with us. He is leaving the ASP, and it is I am heartbroken, and we are going to miss him terribly. I know that all of you at the Night Sky Network will miss Dave like nearly as much as I will. He has been just the heart of the Night Sky Network for a very long time, for over a decade now, and I want to thank him for all that you've done, Dave. It's not going to be the same without you, and those are some really big shoes we're going to have to fill. So yeah, there's a lot of
thank you.
Already
I'll see you all around. But yeah,
we'll invite you back, no doubt, and I'm wishing you the best in your future adventures. And yeah, we'll definitely keep in touch and keep up with you as you go. Thank you so much for your decade of dedication and brilliance, and we'll miss you.
and I'll see all you folks around as I journey around the country. I'll say hi. So yeah, I'll see y'all.
Great. Thanks so much, Dave. All right.
Yeah, thank you so much, Dave. And I think it's not so much that we try to fill your shoes, it's that we're going to have a complete style change. There's no way that we could, duplicate what you do and what you've done.
Well, it's good to get a refresher now and again. Get a different set of stuff for the program. So I think it'll be good. But thank you.
And everybody else, just please be patient with us, because we are going to have a hard time keeping up with what he's been doing. Thanks so much.
All right, for those of you on Zoom, you can find the chat window and the Q&A window at the bottom edge of Zoom window on your desktop. Please feel free to greet each other in the chat, or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. Please reserve the Q&A for your questions. If you do have a question for Brian tonight, please put it in the Q&A. That really helps us keep track of those questions and whether or not we've answered them or not. And I'm going to get the recording started. Again, welcome to the May webinar of the NASA Night Sky Network. This month, we welcome back Brian Day to our webinar. Brian continues to serve as the acting staff scientist at NASA's Solar System Exploration Research Virtual Institute, or SSERVI. He is also SSERVI's lead for lunar and planetary mapping and modeling. In this role, he serves as program office level project manager and science lead for NASA's Solar System TREX project. He's also participated in various lunar and Mars analog field studies in extreme environments here on Earth. He previously served as the education and public outreach lead for the LCROSS and LADDI robotic missions to the moon. In 2007, he flew on NASA's Aurigid MAC mission to record debris from Comet Kais entering Earth's upper atmosphere. And I'd like everyone to welcome my friend and colleague for over 20 years now. Please welcome Brian Day.
Thank you so much. Thank you, Brian. Thank you, Vivian. Thank you, Dave. And thank you all for joining us tonight. We're going to talk about the moon as a destination. And the way that I would like to do that is by looking at it as a series of landing sites. Basically, what we're going to do is we're going to look at the moon in terms of trying to get this to work here. Come on, it's spinning. There we go. So we're going to look at landing sites from the past as well as in the future. And so we'll start out looking at our Apollo landing sites. So between 1969 and 1972, we had 6 Apollo missions actually land astronauts on the moon. And so let's take a look at where they went and some of the reasons why we went to those locations and what we learned from them. Our first mission to the moon was, of course, Apollo 11, the landing site of Mare Tranquillitatis, the Sea of Tranquility. And the moonwalkers in this case were Neil Armstrong and Buzz Aldrin, while we had Michael Collins remaining in orbit in the command module. The place that was chosen was the Sea of Tranquility. It was not chosen because of any particular scientific fascination with this. It was chosen because, as you can see here, the Mare plains are smooth and flat in comparison to the lunar highlands, which are much more rugged and rough. And so we wanted to have the first landing site be as smooth and flat as possible in order to maximize our chances of success. So here you have a nice view looking down at the nice smooth landing lava plains. Everything should have been wonderful. But then the flight computer of the Eagle, the lunar module, ended up taking them down toward this crater here, known as West Crater, which you can see is scattered about with boulders the size of automobiles. And Neil Armstrong looked out the window of the descending lander, realized that they could not land there, took manual control and started flying off to the west. And here you can actually see the actual descent stage of the lunar lander still today. This is as imaged by the Lunar Reconnaissance Orbiter. We can actually see the passive seismometer and lunar laser retroreflectors that they set out on the surface. And if you look very closely, you can see these dark squiggly lines. Those are actually the footprints of the astronauts. So with that success under the belts, Apollo 12 was the next to go. And this went to the area Oceanus Procellarum, the ocean of storms. And that is located, as you can see here, south of the crater Copernicus. And actually the idea here, one of the main goals of this mission was to actually try and determine the age of Copernicus. Copernicus is one of our big markers in the timeline of lunar history. And so we had it as a relative number, but what we wanted to do is get an absolute number for the age of Copernicus. Now, landing in Copernicus was not an option. It's too rough and rugged. But across the smooth plains of Oceanus Procellarum, there's a lot of debris, a lot of ejecta that had been blasted out of Copernicus at the time of its formation. And so the idea was to land on some of that ejecta. Here you can see those light-colored streaks going across the darker plains of lava there. And as a matter of fact, they landed on one of those ejecta rays. In the case of Apollo 11, they were trying to avoid craters. in the case of Apollo 12, they wanted to land right next to some craters so that they could take advantage of the natural excavation that those craters had done and being able to gather a diversity of samples. In addition, they wanted to get around the problems that we had with landing at Apollo 11 and demonstrate pinpoint landing capabilities. You'll see, of course, the lunar module right here on the edge of this crater, but there's another object just inside the rim of the crater. Let's zoom in a little more carefully. Here is the landing stage, the descent stage of the lunar module. And down here, you actually have the Surveyor 3 spacecraft. And so this was actually demonstrating that they could land in a pinpoint manner. They sampled the materials of ejecta and figured out that Copernicus is actually 800 million years old. And they also retrieved equipment from Surveyor that had been there for 2.5 years, and were able to see how that equipment fared in the harsh environment of space. Apollo 14 took a little bit of a different path here. So looking at the moon, we see it landed not in the dark Mare area, but in kind of a transition area. And that transition area, it turns out to be debris blasted out by the formation of the Imbrium impact basin. Again, one of our major dating markers in the chronology of the moon. Now, sometime after the formation of the Imbrium basin, it was flooded by magma and flooded by lava that erased the floor of that crater. And so landing within the bounds of the Imbrium basin would not help us determine its age. It just tell us how old the most recent lava flows were. So what they did is instead they landed to the south in a blanket of ejecta that had come from the Imbrium impact. You can see these rolling hummocky hills here. And this is actually the area that they landed in. So not quite as smooth and as the Mare terrain that we had landed on in the past, but not as rugged as the true highland terrain. But again, the desire was to sample material from the formation of Imbrium. You can see here their traverse path, taking them up a ridge toward the edge of Cone Crater. And as they were approaching Cone Crater, they came upon one of the many specimens that they collected. This is a rock known as Big Bertha, about the size and shape of a football. And Alan Shepard, who was the commander of this mission, looked down, he saw that, and he said, "That's a neat rock, I want it." And it's a good thing he picked it up. It turns out Big Bertha is a breccia. It is a rock composed of many other types of rock that have been welded together by the heat and energy of meteoroid impacts. And fairly recently, in the last few years, one of those clasts, one of those rocks within Big Bertha, was studied in some detail. Actually, a number of them were studied in detail, but one of them stood out. This one class just didn't seem to fit. It was trying to tell us a story. As we listened to that, the story this rock was telling us, what it seemed to be telling us is that it was not a moon rock at all. In fact, what it looks like it was in fact an Earth rock. Now, Earth rocks here, we don't go back all that far. We have wind, rain, and erosion that turn rocks to dust. We have plate tectonics that repave the surface of the Earth. So we don't really have rocks here on Earth that can go back and tell us the earliest stories of those first days of the Earth. But this rock here seemed to tell us that it formed about 12.4 miles down beneath the crust of the Earth, and that it formed about 4.1 billion years ago. Now, during that time, the solar system was a very violent place, and asteroids were slamming into things right and left. And a large asteroid slammed into the Earth, and it blasted material from deep inside the Earth out into space. And some of that material, including this little rock, landed on the surface of the moon. But it did not get to rest there in peace for a long time, because 3.9 billion years ago, another asteroid came, formed the Imbrium impact basin. And from the standpoint of our little rock, it saw this giant tsunami of hot glowing material coming over the northern horizon, burying it and welding it to the lunar material beneath. And there it should have remained buried for the rest of time, except for 26 million years ago, another smaller asteroid came, blasted that cone crater, excavated this little rock, and put it back out on the surface for Alan Shepard to actually discover and bring home. So what we seem to have here is the oldest Earth rock we have ever seen, kept and preserved for us on the moon. Neat story. Apollo 15 actually did venture into the Imbrium impact basin, landing right on the edge, right next to the Apennine Mountains that form the border between the Mare area and the much older, much more rugged lunar highlands. And the idea was to land near the slopes of the Apennine Mountains and hopefully be able to sample some of that ancient material that might have rolled down those slopes. Now, where they landed, as you look here, you see something that looks like a riverbed, but no water ever flowed here. This is in fact Hadley Rill. It was carved by flowing lava, erupted from these vents here in the lower left, and then set flowing out for miles across the floor of Mare Imbrium. And they landed right about there where you see my cursor. And they brought with them, for the first time, an actual lunar rover, so that they would be able to cover significant distances. They were able to drive right up to the edge of Hadley Rill and sample that. But in the background there, you see Mount Hadley Delta. They drove to the lower slopes of that and actually, well, let me not jump ahead. They sampled it and actually did retrieve samples of the ancient or North Acidic crust, ancient highlands material, by far the oldest material that had yet been discovered on the moon. But on the way back from the slopes of Mount Hadley Delta, they were actually running behind schedule, and Mission Control told them to skip their last few stops and make a beeline right back to the lunar rover, or rather to the lunar module. And they were heading back, and on the way back, they saw this. And they decided that, wow, that looks like a really neat rock. We want to get that. But they also realized that Mission Control was not going to allow them to stop. So being smart people, they radioed in that they were having a problem with their seatbelt. And Mission Control radioed back, well, that's a safety issue. You must stop now and fix that. So they came to a stop, jumped out, grabbed this rock, came back, clicked back in, and said, yep, okay, we're back in. Okay, fine, you can proceed. So this sample, which is vesicular basalt, really neat looking rock, is now known as seatbelt rock. Apollo 16 was a completely different type of mission. For the first time, it was decided to venture into that rough, rugged, extremely ancient lunar highland. And so they went to an area known as the Descartes Highlands. And that is, again, well away from the smooth, flat Mare material. And here you can see an example of the area in which they landed. Now, it was thought at one point that this might have exhibited some sort of different type of volcanism, some sort of highland volcanism, but upon landing and cruising over to North Ray Crater, which had done excavation for them and gathering samples, it was discovered that this was actually some of this ancient crust that had formed on the early magma ocean. As things first started to crystallize, you started getting this aluminum-rich crust. And this is what was being sampled in the highlands. Apollo 17, the last of the Apollo missions to go to the moon, carried the first scientist to go to the moon, geologist Dr. Jack Schmitt. And this was a very ambitious mission. This was actually going to an area known as the Taurus Littrow Valley on the edge of Mare Serenitatis, where it penetrated into the lunar highlands. And the Taurus Littrow Valley is actually deeper than the Grand Canyon. So you can see they've gotten a lot bolder here instead of heading for just the safe flat areas. Now imagine flying this approach with towering mountains on either side, flying down into something the depth of the Grand Canyon. And here you can see the actual landing site of the rover from their point of view, looking up at the slopes of North Massif Mountain above them. And one of the things that they noticed right away was you had these beautiful tracks coming down of boulders that had rolled down the face of the mountain. And in some cases, these boulders were actually low enough they could get to them. But by tracing their tracks, they knew exactly where they came from. So that's really good for getting a geologic context. And so here, as a matter of fact, this boulder right here that you see is in fact this boulder now that they're gathering samples of. Now, South Massif Mountain on the south side of this great valley has this beautiful, remarkable landslide material coming off it, extending for kilometers across the valley floor. But in the midst of that light landslide material, there's this dark, dark crater here that had actually been spotted from orbit in earlier Apollo missions. And it was thought that this dark halo around it perhaps indicated that this crater, rather than being of impact origin, was a volcanic crater, and perhaps a fresh volcanic crater with pyroclastic ash deposit around it. So this crater, known as Shorty Crater, was a high priority destination. When they got there, Jack Schmitt was able to determine that it in fact was an impact crater. And that dark material was just the Mare material beneath the lighter colored landslide material that had been excavated and then blasted out onto the surface of the lighter material by the formation of that impact crater. But all was not lost, because as they were walking around the edge of this crater, they started looking down where their feet had been, and they noticed that the shades of gray they had been seeing were now changed, and they were actually seeing bright orange soil. It turns out that orange soil, those were actually beads of volcanic glass that had been erupted in an ancient fire fountain long ago, and again had been exposed by the excavation of Shorty Crater. So here we can actually put ourselves at a vantage point the astronauts never had, but we're sitting on top of South Massif, looking across the Taurus Littrow Valley, and we can see these wonderful landslide deposits beneath us. And their early theory was that these landslides had been actually triggered by the distant impact of Tycho Crater, and some of the debris from Tycho Crater had slammed into North Massif and triggered this landslide. But closer look here, we see there's not just one slide, there are multiple landslides, and they're of very different ages. And so that's hard to reconcile with Tycho being the source of this disturbance. So the question is, what would the source of the disturbance be? And we can see that right here in this dark line going across the valley and actually crossing the landslide deposit. This is the Lee-Lincoln Scarp. This is what we call a lobate scarp. And this is essentially an earthquake fault on the moon. The moon has quakes. The moon has moonquakes. When I first went to school, I started learning that the moon was geologically dead. Well, that's not the case. The Apollo astronauts put seismometers on the surface of the moon and discovered that there are still to this day moonquakes. Moonquakes that get up to magnitude 5.5 and can last more than 10 minutes. And the Lee Lincoln Scarp is an example of a relatively young quake, and we actually see evidence of seismic activity in and around this Scarp area. So after the Apollo program, we had a series of robotic missions that changed our view of the moon in another way. Not only was the moon not geologically dead, but our previous idea of the moon being absolutely bone dry turned out to be wrong, as we realized that, as a matter of fact, there are deposits, even significant deposits, of water ice at the poles of the moon. And that could be a very, very valuable resource for us as we return to the moon. And so we are planning a return to the moon through the Artemis program. We've already had the Artemis 1 mission fly. Artemis was in mythology the twin sister of Apollo and the goddess of the moon. And it's appropriate because with Artemis 3, we will have the first woman to walk on the surface of the moon. But Artemis consists of human landings as well as a series of robotic landings. So let's take a look. Some of these robotic landings are scheduled to begin this very year. And let's look at some of the places we're planning to go with these robotic missions. The first is the Gruithuisen domes. And these are examples of lunar volcanoes. Now let's talk a little bit about lunar volcanoes first. These are not the Gruithuisen domes. These are the Hortensius domes. And you might have to squint really hard and look here to see these kind of small blister-like features here with craters. These are very typical of lunar volcanoes. Very low slope shield volcanoes, slopes oftentimes in the vicinity of 1 degree. This is the result because lunar magma in general tends to be very, very low in silica content. As a result, it has a very low viscosity, about equivalent to olive oil at room temperature. So when that erupts, it's really hard to build a mountain out of that. Now we can change our view to a laser altimetry view and really tease out some of those ups and downs, and those very, very shallow domes start becoming more evident. The Gruithuisen domes are different. Located on the edge of the Imbrium Basin, these are actually tall, steep volcanoes towering thousands of feet into the sky with steep slopes. We don't need laser altimetry here to see them. The lava that erupted here was thicker, it was pastier, it was much higher in silica content. The question is why? Why is the lava here so very different? And the answer is we don't know. But we are planning right now 2 robotic landings in this area. This bay here at the base of the Gruithuisen domes has been recently named Sinus Viscositatis, the Bay of Viscosity, talking about the nature of the lava that erupted here. And this is going to be the planned landing site of Astrobotics Peregrine 1 lander as part of the Commercial Lunar Payload Services program, or CLPS. And so these are commercial partners that will be carrying payloads to various locations on the moon. The Peregrine 1 mission is going to launch on a brand new rocket too, the ULA Vulcan Centaur. So a lot of interesting firsts coming here. And it's going to launch from SLIC 41, Space Launch Complex 41 at Cape Canaveral. This has recently been, this is an old friend of mine. This is where we launched L-Cross from, but it's changed a lot in the recent years. It's being rebuilt now for actual human launches. The upcoming Starliner missions crewed missions will launch from here. So a lot of exciting stuff coming. So a newly refurbished launch pad, new rocket, and a robotic mission to some very interesting volcanoes. Another place we're planning to send a robotic mission is Mare Crisium. Mare Crisium here is on the far eastern side of the moon facing the face of the moon facing Earth. It is an area that is relatively uncontaminated by the Imbrium debris that so inundated much of our Apollo landing site experience. But again, this is a large lava-filled impact structure. And as we look at the surface, we see this wonderful formation here. This is a breached cinder cone on the floor of Mare Crisium. It is known as Horseshoe Crater, and the plan is to land immediately adjacent to that. This time it'll be Firefly is the CLPS provider, the private company that we're partnering with, and their Blue Ghost lander that will land in Mare Crisium. And this is a really small object. I posed it to the amateur astronomy community as a challenge object. I've never seen an Earth-based picture of Horseshoe Crater before, but amateur astronomers are doing wonderful things right now, and I got amateurs coming back with beautiful images actually capturing Horseshoe Crater. So cool stuff. There you can see another image of it. So consider that a challenge object. Go after Horseshoe Crater within Mare Crisium and be ready to be observing it when we have a upcoming landing there. Another area that we're targeting is Reiner Gamma, which is a classic example of a lunar swirl. And so here you see this strange tadpole-like feature. This is strictly an albedo feature. It doesn't have any topography to speak of at all. It is just an area of light and dark. And as we get closer, we see these sinuous swirls here. And these examples of what we call lunar swirls tend to be associated, in fact, they are all associated with localized magnetic fields on the moon. The moon itself does not have a global magnetic field the way the Earth does, but it does have relic localized magnetic fields. And this is what we seem to be seeing here are the tracings of those magnetic field lines in these areas of light and dark. Very similar to if you've had the experience of taking a piece of white paper, putting it down on top of a bar magnet and sprinkling mountain iron filings on top of the paper. You can see the tracing of the magnetic field lines. That seems to be what we're seeing here. Of course, the big question is, why is there a localized magnetic field here? And again, the answer is, we don't know. That's a very strong motivation to go here and explore. And so we will be doing so with a lander from another CLPS partner, Intuitive Machines. And this will be the IM-3 lander that is scheduled to land in the swirls of Reiner Gamma. But as you have heard, a lot of our activity in the Artemis program is going to be centered in the region of the South Pole. And so let's take a closer look at the South Pole. The South Pole actually occurs on the rim of Shackleton Crater. And Shackleton is one of these examples of a permanently shadowed crater. And it is, again, its floor has not seen sunlight in literally billions of years. Shackleton measures about 21 kilometers across and about 4.2 kilometers deep, roughly 3 times as deep as Earth's Grand Canyon. But the temperature down at the floor of that crater is not many degrees above absolute zero. So here you can get a view of the depths of Shackleton Crater. We are not planning to land in Shackleton Crater. However, our first South Polar landing will occur in an area that will be the furthest latitude we've yet experienced, the crater, the ancient degraded crater Malapert A. And you can see Malapert A right in the center of the field of view there. It's not much of a well-preserved edifice of crater hoodliness, but it is, in fact, again, a great place to go to test operations from extremely high latitudes, in this case, in the southern hemisphere. So this will be the Intuitive Machines IM-1 mission, again, part of CLPS. And this will occur in an area that is on the edge of Shackleton Crater. And I'm having trouble. I've got, of course, my Zoom controls now right in the middle of everything. See if I can move it here. So there we go. So on a ridge connecting Shackleton and de Gerlache craters. And this is, here you can see Shackleton in the foreground, de Gerlache in the background. This is also one of 13 candidate landing regions for the human Artemis missions. We haven't decided exactly where the humans are going to land first, but we have 13 candidate regions, and 2 of them lie along this ridge here connecting Shackleton and de Gerlache. The ridge has nice, smooth, flat areas that should be safe to land, but it also has a number of small, permanently shadowed craters that would be immediately accessible to our astronauts landing there. The Intuitive Machines CLPS mission IM-2 will actually go to this connecting ridge before we send people there. So the IM-2 mission is scheduled to go to the Shackleton de Gerlache connecting ridge. Another potential landing site for our Artemis missions, there are 2 regions right on the edge of de Gerlache crater. And here you can see de Gerlache. It is about 33 kilometers across and 2 kilometers deep. You're actually seeing detail in here that normally you wouldn't be able to see. What I've done here is I've actually blended optical imagery and laser altimetry, giving us a view of the inside of the crater. The astronauts will not see this kind of detail. They'll see bright and dark. Another area that is a potential landing site for our Artemis astronauts is the de Gerlache-Kocher Massif. And this is a mountain standing, actually this is the furthest furthest into the far side of any of these 13 areas. And this mountain rises over 5 kilometers above the surrounding terrain. Now, as I mentioned, this is actually beyond the limb technically into the far side of the moon, but because of the altitude of this peak, you actually still will be able to maintain communications with the Earth. And also the altitude provides sunlight, good sunlight for power and being able to navigate around in brightness. Now, yet another of our areas is on the edge of the crater Haworth. And we have Haworth in the foreground here, but where we're thinking of landing is actually in the rolling highlands between Haworth and the ridges of the Malapert Highlands in the distance. And these actually are a little bit smoother than some of the other rugged terrain here and have good opportunities for traverses, for exploring permanently shadowed areas, and maintaining communications with the Earth. I mentioned the Malapert Highlands, and that specifically we're going to look at Malapert Massif. We mentioned the permanently shadowed areas on the moon, areas where the sun hasn't shone for so long, and you have accumulations of potential accumulations of water ice. But the south pole of the moon also has tall mountains that stick up high enough to get almost constant sunlight. Malapert Massif has been referred to as the ridge of eternal light. That's a little bit of a misstatement. There's no area on the moon that receives constant sunlight throughout all seasons, but Malapert gets a lot of light for a prolonged period of time. And this is great when you're thinking of having sources for solar power. On the general, more equatorial regions of the moon, where we were with Apollo, you typically have 2 weeks of day followed by 2 weeks of night. And that 2 weeks of night is a real problem. Surviving the lunar night is not easy. But having an area where you have nearly constant sunlight, therefore a constant source of energy, and having that right next to areas of permanent shadow makes Malapert Massif an attractive option. Another area we're looking at is Faustini crater. And, or no, excuse me, we're not there yet. We're looking at a peak near Shackleton. Again, we're not going into Shackleton, but just off to the side of Shackleton. Shackleton's in the foreground here at the bottom of the image. You see this nice rounded peak towering up above Shackleton. And again, that towering peak gives us access to sunlight, access to Earth communications. But again, you have a wealth of small permanently shadowed craters around the rim of Shackleton. So this could be a very interesting site to land. And then, as I was trying to jump the gun earlier, we have the rim of Faustini crater. And so we're looking at Faustini right here. Again, I'm blending visible light with laser altimetry so we can actually visualize the crater. The landing site, the landing regions we're looking at are on the poleward rim of Faustini, this area here that's illuminated. Faustini measures about 39 kilometers across and 3 kilometers deep. Another area that we're looking at is a very spectacular site right on the rim of this large crater here, Amundsen. Amundsen is a great South Polar landmark. It's more than 100 kilometers across, about 4 kilometers deep. It has these beautiful central peaks rising 1.25 kilometers up. The area that we're looking to land is near the rim of Amundsen. This is the earthward facing rim, the earthward side of Amundsen. And then finally, we're looking at areas along this crater here is Nobile crater. And Nobile crater is located on the slopes of a mountain that used to be known as Mons or as Leibniz Beta. But it is now recently, just very recently, been renamed Mons Mouton. And here you can see Mons Mouton, a flat-topped, very massive mountain. From the summit of Mons Mouton down to the floor of Shoemaker crater at its base measures 6.2 miles, 10 kilometers in height. So this thing is taller than Mount Everest. And you can see this steeply tilted Nobile crater on the edge of Mons Mouton. Two of our potential landing sites for Artemis, human Artemis landings, are on the edge of Nobile crater at right along the summit plateau. And then another one of the potential landing sites is along the lower rim of Nobile. But on the near Nobile at the top, at the summit ridge, we're also planning to send a robotic probe. This is the Viper rover. And Viper is being developed right here at NASA Ames. And it is designed to actually cruise across the summit plateau of Mons Mouton, prospecting for water ice. It has a neutron spectrometer, it has a drill. It's going to be mapping out the distribution of subsurface water ice, and it's actually going to drive into one of those incredibly frigid, permanently shadowed regions. It will be delivered to the surface of the moon by an astrobotic Griffin lander, again, as part of the Commercial Lunar Payload Services program. And continuing now to the further side of the moon, we're looking at going to, well, looking at the far side of the moon here, again, a laser altimetry view. Now what we're doing is we're color coding it so that the purple areas are the lowest areas, blue a bit higher, green a little higher still, orange are the highest areas. And what we can see here is this great, huge impact basin on the far side of the moon. And this is known as the South Pole Aitken Basin. And it is measures about 2,500 kilometers across and perhaps over 8 kilometers deep. This is interesting to us because that means it might actually have been able to sample down into the mantle material of the moon. We would love to examine mantle material. Drilling that deep probably is not feasible anytime soon, but Mother Nature may have done that for us. So what we would like to do is actually land in a place where you have this South Pole Aitken Basin. You can tell here it's very, very ancient. It's been terribly eroded. It's 4+ billion years old. But what we'd like to do is find one of these newer impact sites in the SPA, the South Pole Aitken Basin region, that will have excavated down into that and get us into perhaps some of this very interesting material. And so one of the areas we're looking is the Shackleton crater area on the edge of the South Pole Aitken Basin. And here we'll get a closer look at Shackleton crater It is a really beautiful crater. It's big enough, instead of having a central peak, it has a central ring. We can see fractures on the floor, areas where part of it was flooded with marine material. We can even see here a volcanic pit crater surrounded by a pyroclastic deposit. And this pit crater here is far enough south that it's actually, part of it is in permanent shadow. I mean, there's a lot of cool stuff going on in Shackleton. And there's a view of that volcanic pit crater. Pretty exciting stuff. Shackleton is the target of an upcoming CLPS mission. This will be a lander provided by Draper, one of our CLPS partners, commercial partners. And continuing with the lunar far side, we are looking at the lunar antipodal region directly opposite the Earth on the surface of the moon. And a probe that we're looking to send there potentially is the Lucy Night mission, the Lunar Surface Electromagnetics Experiment. The far side of the moon is very special to us because it is unique in the solar system, being constantly pointed away from the Earth and shielded from the Earth by huge numbers of kilometers of solid rock. The Earth puts out immense amounts of radio noise thanks to us, and that noise could swamp out very, very faint radio signals from the earliest days of the universe, from what we call the dark ages, as the first stars began to turn on. And we would love to be able to detect those signals. And the far side of the moon is probably the best place in the solar system to do that. Again, pointed away from the Earth, shielded from the Earth by the thick layers of rock of the moon. And so the plan is to, what people are proposing is to actually put radio antennae, even large dishes inside of craters, to actually be able to study the earliest times of our universe. Now, a lot of the visualizations that you've seen here tonight, I generated with a series of portals that my team at NASA has come up with. These are the NASA Solar System Treks. These are web-based portals that allow you to explore the surface of the moon and other worlds as seen through the eyes of many different instruments on many different spacecraft. Looking at the Moon Trek portal here, you can see how we can, like any good GIS, we can pan, we can zoom in here, look at the crater Tycho. You might want to know how deep is Tycho, or how large is Tycho. Measuring a distance, a diameter is as simple as drawing a line. So we can measure Tycho here and see that it's over 80 kilometers across. That's a big hole in the ground. We can also then answer the question, how deep is Tycho? We have an elevation profile tool. So again, as simple as drawing a line across Tycho, this time we'll extend on either side of the crater, catch the rim, and we can generate an elevation profile. Here we'll scoot Tycho to the side, and we can actually, you can see how we can measure the heights of mountains, the depths of craters very, very easily. We can also do fun things like draw a bounding box around any terrain that we like. So we can just draw a nice rectangle here around Tycho, and we are given the option of choosing between an STL or OBJ file, so we can make 3D prints. If you've got a 3D printer, you can make 3D prints of any terrain you like. We can also switch into 3D globe mode, interactive flying, so you can interactively go flying across the surface of the moon, fly down into craters and go roving across the surface. It's a lot of fun. You're also able to use your mouse to draw a path anywhere you want on the surface of the moon. The portal will then return a QR code to you that you can scan into your smartphone, either iOS or Android. Put your smartphone in a pair of cheap $5 Google compatible goggles. Whatever path you drew, you will now fly in virtual reality. You create your own virtual reality adventures. You can drag outlines of any state or any country onto the surface to do size comparisons. There's all kinds of wonderful things you can do. Again, this is all web-based, all browser-based. You don't buy anything, you don't install anything. Just point your browser to trek.nasa.gov. And with that, if I have not rendered you all unconscious, I will attempt to take any questions you may have.
All right, thank you, Brian. I'm trying to get the URL into the chat there. We had a number of people ask for that, so I think we got it. And actually, I was going to kind of set you up with this question. We had a couple of questions earlier about images were fantastic. Where do we find them? And then a follow-up, can you give us a scale of miles on those? But you showed us exactly how you can do that yourself with Moontrek, and
Yeah.
Fantastic. So we had a couple of questions having to do with a number of people were speculating about, this is great that we're going back, but why has it been so long since we've been there? Although we've been there with robotic missions, and it's taken us a little while to get humans back there. And so a number of people have been.
Yeah, it's taken us a lot longer than a lot of people ever thought. It's been a long time, but it's, this has been a matter of societal priorities. And we had not had the priority of going to the moon until more recently. Part of that too is because we did not realize the potential that the moon has. Until we realized the resources that were available on the moon, going to the moon seemed like, going to an expensive effort to go to a very desolate desert place. But we now realize that the moon is rich in resources, rich in ice that can be broken apart into hydrogen and oxygen, and that can be used as fuel to take us to more distant places throughout the solar system. Launching from the moon is far easier than launching from the Earth in terms of the gravity well, in terms of the lack of atmosphere. There could be a lot of advantages to using the moon as our launching spot and gas station to the rest of the solar system. Also, there are a number of, we now realize, interesting resources on the moon, including significant deposits of rare earth elements. So you can actually now, after the science that has been done post-Apollo, we can now actually make a credible business case, an economic case for going back to the moon.
So kind of going along with that, and so this is kind of a fundamental question about, why send humans there? What science will the human missions accomplish that could not be accomplished by the robotic missions? What makes the human missions worth the additional complexity and cost?
It's a great question. We get asked that all the time, and we hear a lot about AI. We make use of AI in the solar system treks significantly. We've got a number of tools that I did not demonstrate tonight. I should point out the solar system treks, Moontrek and its sister portals, covering other worlds throughout our solar system. These are mission planning tools. These are tools that are used to analyze landing sites, to plan potential rover traverses, and we do make use of a lot of artificial intelligence and machine learning. But there are still things that we are just not able to do remotely through robots that we can do with a trained scientist on the moon. At this point in time, it's not a question of humans or robots, it's a matter of both. And what we're looking at is ways to have them interact with each other and actually have robotic explorers alongside human explorers and interacting in a way that provides synergy that is better than either working alone.
All right. And we are over 7 o'clock, and so we recognize that many people are going to need to leave. But we're going to keep going just for a few more minutes, if you don't mind, Brian.
I'm happy to.
So you've alluded a lot to the water, and so that there's a lot of water up there. And so we had a couple of questions about, well, just how much water are we talking about? Enough to cover the entire surface?
So we realize that there are essentially billions of tons of water ice. And beyond that, we're also realizing that there is water that it was actually originating from the interior of the moon that is actually now entrained within pyroclastic deposits on the surface of the moon. There's water apparently that forms from the solar wind, those hydrogen atoms moving at high speed, slamming into the silicate atoms on the surface of the moon. There are a number of ways that water can arise and a number of places to find water on the moon. But what we still don't know, well, we know there are large quantities of water on the moon. We don't know how that water is distributed. We don't know what its accessibility is. We know that there are water deposits, but we don't know just how usable they are as resources. This is the entire purpose of the very, very long-term process of prospecting, something we've done here on Earth over and over again. And this is what, for instance, Viper is designed to do. It is prospecting. It is looking at, it is determining how is water ice at the South Pole actually distributed. That's a big question we need to answer to really be able to then figure out how we will be able to, what kind of effort is going to be required to be able to access and potentially use that water on the moon. We have to go through that vital step of prospecting.
So there's a lot to unpack in what you just said. And let me see if there's a couple of questions that maybe can illuminate this. And one of the things I didn't realize that a lot of the water is now thought to have come from volcanic activity. And a lot of people might think that, well, it comes from comet impacts. And
there's certainly a good deal of them. So, what is the nature of water? Where all did it come from? We want to get some of these samples. We need to get some of these samples to really better understand the resource or the potential resource there. Certainly, a lot of the water or some significant fraction of water probably did come from cometary impacts. Also, you have types of meteorites that are rich, relatively rich in water, a number of the carbonaceous chondrites. But then you also have, so you have those exogenous sources. Another exogenous source, again, is that solar wind. But you could have endogenous sources, that the material that the moon formed from, likely those original, there was probably originally a lot of chondritic material smaller masses coming together, and there was probably significant water content in that. And so we realized that the interior of the moon probably is not completely dry. As a matter of fact, we now know that to be the case. We look at some of these pyroclastic deposits, some of those beads of volcanic glass that came back from Apollo 17. We realized that some of these volcanic beads of volcanic glass actually contain these essentially crystalline cases that deep magma that had been erupted into the lunar sky, but then had been protected from outgassing by being in these crystalline cases. And if you go in with ion microprobes and you pull some of that material out, you see that there's actually a surprising amount of water in that relatively pristine lunar magma, at least in some locations.
So that kind of brings up another question. A lot of times it's a surprise to many people that there's volcanic activity on the moon. And we did have a question that they were asking, is the moon's core molten? Is there a metallic core? And it really kind of speaks to differentiation within the moon's internal structure, which it sounds like that's fairly integral towards understanding what's on the surface and the resources and what we're trying to discover.
Yeah, we realize that the moon is a differentiated body. It has a small metallic core, much smaller than the Earth's. That speaks to how we think the moon formed, along with the Earth in a giant collision long ago. We believe that body about the size of the Earth and a body about the size of Mars both tried to occupy the same place at the same time with predictably messy results. Both of those worlds were severely damaged. The majority of the dense, heavy nickel iron cores of both of those worlds sank together and formed the especially large metallic core that the Earth has today. But some of the material was blasted off into space, especially outer lighter material from both of those worlds. Some of that material was lost to space, but a lot of it formed actually a ring around the early Earth. The Earth had a ring around it, much as Saturn does, but unlike Saturn's ring, which is made of ice, the Earth's ring was made of molten rock. And over time, that molten rock started to clump together and it formed the moon. Understanding that made us think that probably a lot of the volatiles, a lot of the water should have been driven off in those extreme temperatures. But we're finding that that may not necessarily be the case. So we're having to fine tune our understanding of the moon and how it formed based on the materials that we are finding there, and coming back with far more lunar samples from a far wider range of locations across the moon than we have ever been to before will only help us gain a better understanding.
And I think you just answered one of the questions, the next one that I was going to pose, or related to another one about expounding on the source of the moon. I think you just answered that one, so thank you. We had a very early question that, and we're just going to go for a couple more questions here. Which mission discovered the Genesis rock, and why was that an important rock to our understanding?
So that was Apollo 15. And Apollo 15 was, up until that time, we had not approached the lunar highlands. Apollo 15 did not land in the lunar highlands, but it landed right next to them on the slopes of the Apennine Mountains. So you had landed on the flat lava plains of the Imbrium Basin, but you had then had this ancient highland crust, this anorthositic crust So we talk about different types of rock on the moon. When you look up at the moon, just in the sky with your unaided eye, you see the dark, flat plains of basalt. In the lighter areas that you see, that's the rugged highland crust. That's largely made of a lot of what we call anorthosite, a much rarer rock here on Earth, but quite common on the moon. And this is, again, that really ancient early crust that formed as you start having solidification of an early magma ocean around the early moon. The Apollo 15 astronauts drove up the lower slopes of Mount Hadley Delta, looking for pieces of that highland material that might have rolled down and become accessible to them. And one of those, they found just such a rock, and that was because this was anorthositic. This is part of that ancient crust, as opposed to the more recent basaltic material. This ended up being the oldest rock that had been recovered to that time on the moon.
All right, and I think with that, we're going to have to stop. And thank you, everyone, for all these really great questions. I'm sorry that we weren't able to get to any more. But this is really, really great stuff. And so that's all for tonight, everyone. Thank you, Brian, for joining this evening and hanging in there for a little bit longer with some of these questions. Thank you, everyone, for tuning in. And you'll be able to find this webinar along with many others on the Night Sky Network website, as well as the YouTube channel. Join us for our next webinar on Thursday, June 22, when Kristen Weaver from the Globe Eclipse team will join us to show how we can participate contributing to NASA eclipse science through using the Globe Eclipse module in the Globe Observer app. So keep looking up, and we'll see you next month. And I'm going to put a link to the survey. And if you fill that out and then get to the end, we'll be in a drawing, and we're going to send out 5 copies of the book Totality that Vivian mentioned at the front of the webinar. So